In this video, we solve problem 11.5.096 from the Larson and Edwards Calculus Early Transcendental Functions text, 7th edition. We're asked to find the distance between the point and the line given by the parametric equations, and then we're asked to round our answer to 3 decimal places. For this and any similar problem, I recommend starting by drawing a sketch of the situation. Because this line is in 3-dimensional space and this point is in 3-dimensional space, we probably can't graph that accurately in any way that's really going to be insightful to us. So instead, we're just going to draw a cartoon. We're going to say we've got some point Q over here, and then we've got some line over here. And the question is, what is the distance between this point and this line? Now, there are infinitely many distances. You could say, well, what about, are you talking about this one? Are you talking about this one or this one? What we're talking about is the shortest distance between Q and the line. So that is the length of this little line segment, where that line segment meets the point Q and the line at a right angle. So that's what we're looking for. Now this is actually relatively easy to find. If we have a point P on the line, and we can find a point P given these parametric equations, and we have the direction vector V of the line, we can also find that direction vector using these parametric equations. This is enough information for us to find that distance. If you're asking yourself how, well, if I can find P and I know the point Q, this is our Q in this particular example, I can draw a vector from P to Q. Then the angle between the vector PQ and the vector V, is called theta. And then just using right triangle trig, that shortest distance that we're looking for is the shortest distance between Q and the line, is given by the magnitude of this hypotenuse, which is the magnitude of the vector PQ. And then since that side is opposite theta, we have a sine of theta. Now we don't actually know theta, so we don't want to use this formula, but we do have enough information to find P for given Q. We can find V. So we'd like to write this answer for the shortest distance, not in terms of theta, but just in terms of P, Q, and V. In order to do that, I can say to myself, well, that kind of looks like the magnitude of a cross product. The magnitude of a cross product has those two magnitudes times the sine of the angle between the two vectors. So I've already got the magnitude of PQ here. The only thing that's missing is the magnitude of V, and now that is the magnitude of the cross product of the vector PQ with V. If you're saying to yourself, how can you do that? Well, you can't just do that. If I want to multiply by that, if I want to keep this quantity exactly the same, I need to divide by it as well. So the shortest distance between Q and the line is given by this formula. So it looks like, well, we've got almost everything we need. We know that this is Q. And then with these parametric equations, we can find the point P, and we can find the direction vector V, or a direction vector V for that line. And then once we have P and V, we can compute PQ, we can take this cross product, we can find its magnitude, and then we can divide by the magnitude of V. Very simple. Okay, so let's start by finding P and V. So remember when we talked about lines, we said that the parametric equations of a line could be written this way. X equals x naught plus at, y equals y naught plus bt, and z equals z naught plus ct. And this is where the line passes through a point x naught, y naught, z naught. So x naught, y naught, z naught is on the line. And the line has direction vector. ABC. or it's a direction vector with components A, B, and C. So using that and then just pattern matching to this, x equals 2t, y equals t minus 3, and z equals 2t plus 2, I can see immediately that x naught, y naught, z naught, those are the constants here. On this first one, I don't have a constant. I could just add a 0. X naught, y naught, z naught could be given by a 0, a -3, and 2, just through pattern matching. If you're saying, well, why didn't I choose those? Those are multiplied by t. And then the direction vector v has components that are given by the coefficients of t over here. So I see the coefficients of t are a, b, and c here. In our case, there's a 2. And then here we've got an implied 1. And a 2. So our direction vector v is given by 2 times I hat plus 1 times j hat plus 2 times k hat. So that's one way that we can do this. Another way that you can find x naught, y naught, z naught is to just plug in any value of t to these equations. I know I've highlighted them a lot, so it's a little bit less clear at this point. But if I plug in t equals 0, like I can think of that as representing a particular time. I might say to myself, if there's some particle traveling along this line, and at every time it's at a different location given by x of t, y of t, and z of t, where will that particle be at time t equals 0? Well, I could just plug t equals 0 into here, and I get x equals 2 times 0, which is 0, y equals 0 minus 3, which is -3, and z equals 2 times 0 plus 2, which is 2. It's exactly the same point that I end up at, 0, -3, 2, that I end up at if I'm just pattern or recognizing that pattern here. So that's one way. Now you could also plug in t equals 1 if you wanted to. You could say x equals 1, or 2 times 1, which is 2, y equals 1 minus 3, which is -2, and then z equals 2 plus 2, which is 4. That's another point on the line. So by choosing a value of t and then just seeing what x, y, and z would be, that'll give you a point on the line. Or you can just recognize the patterns. Okay, so this is our x naught, y naught, z naught, which we're going to label as the point P, and we've got a direction vector v. So once we've identified P and V, we can use P and V in the point Q, which was given to us. It has coordinates 6 and -8 and 4. And we can use those to find the vector PQ, and then take a cross product with V, and so on. Okay, so our point Q is this. From that work we just did, we said that P would be any point on the line. We chose this point on the line. And the vector V has components 2, 1, and 2. Next thing we want to do is find the vector PQ. Now remember how we do that. We take the coordinates of our terminal point, which are 6, -8, and 4. And then we subtract the coordinates of our initial points. That's 0, -3, and 2. This is what we get. We get 6. And then, of course, that y component is -5. All right, so there's PQ. And now remember what we wanted. We're evaluating this formula to find the distance between that point and the line. So I found the vector PQ. Now I want to compute the cross product of PQ with the vector V. So if we use this determinant form, we list I hat, j hat, and k hat in the top row. PQ's components go right there, and the vector V goes down here. Then remember, we cross out the row and column containing I hat, and then we evaluate this 2 by 2 determinant. You don't have to write down this step. If you want, you can do that in your head, and that'd be fine. And then we cross out the row and column containing j hat. We have a minus j hat times. Then we have the value of this 2 by 2 determinant. We've got 6 and 2 in the top row and 2 and 2 in the bottom row. And then we cross out the row and column containing k hat, and we multiply by this one, that 2 by 2 determinant. And so we've got I hat times a number minus j hat times a number plus k hat times a number. And I'll just figure out what those numbers are now. Remember how this works. When you're evaluating a 2 by 2 determinant, you multiply across this diagonal and that diagonal and subtract. So we'll have A times D minus B times C in general. We've got negative 10 minus 2. Then we have negative 1 times 12 minus 4. And then here we've got 6 minus a negative 10. And so we get negative 12 for our x component. This will be 8 times negative 1, so it'll be negative 8 for a y component. And then adding or subtracting negative 10 is the same as adding 10. So we've got 6 plus 10, which is 16. All right. But we don't actually want the vector, we want the magnitude of that vector. So now let's find the magnitude of this vector. Easy breezy. And if you're saying to yourself, why do you write 2 vectors there as opposed to 1 vector there? Either one works. If I take the vector PQ and I cross it with a vector V, I end up with a new vector PQ cross V. So either one is fine. If I want to find the magnitude of any vector, I take the components, I square them and I add them, and I take the square root. Easy breezy. Of 12 squared plus 8 squared plus 16 squared. Take the square root of your answer, and we get 4 times the square root of 29. And we'll just leave it as an exact answer for right now. Okay, now the last thing we need, or one of the last things we need, is the magnitude of V. And then we'll take this magnitude and that magnitude and we'll divide them, and that will be the shortest distance between Q and our line. So we're 2 steps away from answering our question. So our vector V had components 2, 1, and 2. So the magnitude of V is given by this. So you've got 4 plus 1 plus 4, square root of 9, which is 3. All right. Final request is to take PQ, or the cross product of PQ and V, its magnitude, and divide by the magnitude of V. So the distance, the shortest distance between Q and our line, is this magnitude divided by that magnitude, which turns out to be this. Now they want us to round to 3 decimal places. So I've already got that in there. I'll divide by 3. And then I just use this SD button on my Casio calculator. It's going to be 7.180 approximately as our distance. Okay, so briefly, let's go over this. The distance between a point and a line is given by this formula, where P is a point on the line, Q is the point that they gave you, and V is the direction vector of the line. Now, if they don't give you a point on the line in the direction vector, but they give you parametric equations, you can always find a point on the line by substituting in any value you want for t. Usually if we substitute in t equals 0, we'll get this point x naught, y naught, z naught. Well, actually, every time we substitute in t equals 0, we'll get this point x naught, y naught, z naught. That'll be our p. And the direction vector v is given by the coefficients of t in these parametric equations. So v has components a, b, and c. So we just identify a, b, and c. We identify x naught, y naught, and z naught. That gets us p and v. Okay, so now we've got a point on the line and we've got the direction vector for the line. Now we compute the vector PQ, we did here. Take the terminal point and subtract, or the coordinates of the terminal point and subtract the coordinates of the initial point. Then we want to compute the cross product. And then we want to find the magnitude of that cross product. A distance should not be a vector. A distance should be a scalar. So we're going to find that scalar, that magnitude of that cross product. And then we find the magnitude that we need for the denominator. And then we just divide those to get the shortest distance. And then I would type this if I was looking for an exact answer, but WebAssign wanted a decimal approximation. So that is our decimal approximation.